Okay. All right. Welcome back. This is week three of the discussions that we are having, and I hope you guys are liking the course and the assignments associated with it. Uh, First of all, thank you for actively participating in the discussion forum. And today the agenda is, so what we will do is, as there were certain questions associated with the previous two assignments that I think you guys have submitted the assignment, but nevertheless, uh, there were certain clarifications that were supposed to be made in some of the questions that I received over the emails in the discussion forum, and also the emails uh, that were sent to me, is that some questions in the assignment needs clarification, and I thank you all for like bringing them to me. And so what we will do today is we will start off by discussing those certain questions that I believe you need a further clarifications. And then once that is done and the doubts are cleared, we will move ahead with the discussions of this week, which is basically an extended version of the discussions which we had in the last week. So if you remember, in the last week, our domain of interest was essentially planar. So the flows that we are looking at was something which is called as which we generally call as the steady rectilinear one directional flows. Today we will just add a little bit more complexity, which is something. So what we will look into is something, we will still be sticking into steady one directional flows, but now at least once we discuss the questions of the assignment, after that we will look into something which is known as axisymmetric flows. For instance, one of the most common examples of axisymmetric flows is flow through a pipe. You must have learned that in your undergraduate fluid mechanics classes, is that so whenever there is a liquid flowing through a pipe, there is something which is known as a developing region, and then there is something which is known as a fully developed region. We will mostly stick into the other the later one, which is the fully developed region, and do the Navier-Stokes, and write down the Navier-Stokes analysis which govern the flows in that so-called fully developed region. And these kind of flows that happen through this, so it can, so there could be a flow flowing through a pipe, or it could be a flow that can be taking place through an annulus, that is between two concentric pipes, and things like that. So such kind of flows are known as axisymmetric flows in the literature. And we will look into one example that is associated with these flows, and through this example we will I believe things will be clarified in uh, that you are supposed to learn in with regards to axisymmetric flows. Okay, but before that, we will basically hold on. Okay, so before that, we will basically look into some of the problems that came as a doubts while some of you guys were solving the assignments. And again, I thank you for like bringing that up, and please actively participate in the discussion forum. And this helps us as well as you to be on the same platform in terms of the learning that we are doing. Okay, so this is a problem. Okay, this is a problem that was in assignment one. I'll write it down here. So this was a problem, so I just took the snap of this problem from the website. So I think these problem this so by the way, the answers of the assignments 1 and 2 are already shared to you. I hope you have at least gone through them, and although we will discuss this problem, but at any point of time you can always look back at the answer, and reflect on where you have possibly made a mistake, or where things could might have gone wrong. That will always be done, like after you submit the assignment, the answers as well as the detailed explanation will be shared to you. But nevertheless, we will again discuss this in the discussion forum, because that is the sole purpose of this interaction, right? So that's the idea. So having said that, let's not waste any further time, and just let's get started. So this is a problem in assignment 1, where you are asked basically to calculate what is this velocity u naught. Okay, now we'll look into this problem. I hope you can see the problem in my screen. I hope this is visible. So it says that, remember, we did a similar problem, not exactly of this sort, but I gave you a hint that there is a similar problem that we'll also find in the assignment, and this is exactly the problem that I was talking about. So let's have a look what it says. So it says that water flows through a constant head tank. So remember this. So certain keywords are important in this problem. It says that the head is constant. Okay, as shown in figure 1. Figure 1 is, of course, you can see it in my screen. Okay. So the fluid is entering into the tank with a uniform velocity u infinity. So this is where, the water is entering into the tank. You can see from the direction. I hope the arrows are not so if you zoom in, you can see that the arrow is basically pointing inward into the tank. Okay, which means through this section, which means that through this section there is a fluid that is coming in, and the word says, so what the question says is that it's a constant head tank, which means that the water level inside this tank is not changing with time, and this is typically what the constant head actually means. Okay, the problem that we solved in the first, if you remember, the problem that we solved in the first interactive session is that there was a constant inflow of the fluid that was coming from the two sides of the tank, which means that since there is just a net inflow and no outflow, the height of the water level inside the tank was changing with time. On the contrary, in this problem, what it said is that the height of the water level is not a function of time. Okay, this is the basic difference that was that this problem and the problem that we solve in the first week. So this is where the difference lies. Okay, so this means you must realize now that in order to make the head of the tank constant, that is in order to maintain a constant head inside the tank, it must so happen that the net inflow should be equal to the net outflow. This is only so at this point only you can maintain a constant head inside any container. This is something that you need to realize, which means there also had to be a net outflow, which is, let's say, taking from this particular section. Okay, summarizing, what it says is that there is a tank through which fluid is coming in. Let's say we name this section A. From section B, there is a fluid. I mean, the same fluid is going out, such that the height of water inside the tank, let's say this is the height. Okay, this is made constant, and this is not a function of time. If the rate of inflow, you must realize that if the rate of inflow and the rate of outflow is not the same, then h will be a function of time inevitably. Okay, that is just the simple mass balance says, and in fact we will apply mass balance to basically calculate what is being asked in the question. So what it says is that the fluid is leaving with a velocity u. The only difference is that the leaving velocity profile, instead of it being a constant, this is now a function of the local y coordinate, which is y1. And this is also something that I have hinted in the first week when we solved this problem. So remember, in the problem that we solved, we said that the two inflow rates, okay, were of the same. So the velocity profile was just constant. But in this problem, the outflow profile, instead of it just being a constant, it is a more realistic scenario where the outflow profile is essentially parabolic in nature, and it depends as a square of the local y coordinate, which is y1. Because you can see here that the velocity profile is just proportional to minus of y1 square. That is something that you can appreciate. Okay, and as I said, this is a more realistic representation of the velocity, because this particular velocity essentially satisfies something which is known as the no slip boundary condition on this and this. Okay, so I hope this is clear up to this point. Okay, so there is an inflow, the velocity is constant, which is u infinity, but the outflow, the velocity profile is parabolic in nature. The height of the tank is constant. This is given to that is basically given to you, and it says that the width perpendicular to the plane of the paper is b, which means that the width of the tank is basically equals to b. So it says that this is basically equal to b. You can take b as a constant. That's it. Now, having said that, and given that this u infinity has got a magnitude of 11 meter per second, they are just asking that what is the magnitude of the outflow velocity, because you can see that the outflow velocity, because you can see from here that the outflow velocity has got a form u naught into 1 minus y1 square by h square. I would say the direct, because since velocity is a vector, I would say it's in the direction of, so you can say that this is basically in the direction of this vector. So I would call it as, let's say I would call it an e n1 hat. Or let's say, let's not just call it as en1. It just says that the unit vector in this direction is n1. So I can safely say that my velocity is in the direction of n1 hat. Is it clear up to this point or not? Can you just give it with a yes or a no, that so far, like, is it clear what the problem is saying, or
Uh,
there are still some doubts? Yeah.
yes, sir. This is clear.
Okay, sure. Uh, I'm audible, right?
Yes, you're audible.
Yeah, yeah. Okay, okay. Just hold on. My actually this just 1 second. Think my microphone is just not working. Hold on. Okay. All right. Can you just tell me now that I'm audible or not? Just tell me.
Yeah, it's very
Yeah, yeah.
clear, sir.
Yeah, yeah, sure. Thank you. All right. Okay, so this is what they're asking. Sorry for the interruption. So this is what they're asking is that you just need to find out this magnitude of u naught. So what shall we do? See, the problem that, again, I'll come back to the prototypical problem that we solved in the first part, because that problem, so this problem actually builds up from that problem. And I hope you realize what is the difference between this problem and the one that we solved in the first interaction of this course. Okay, so there are a couple of things that you need to understand. First, in that problem, there is a net inflow of the fluid, which means that since there is just a net inflow and the fluid cannot go out, and we assume that there is no spillage and all those things, the height of the tank would basically rise with time, which means that problem was an unsteady problem. On the contrary, if we look at this problem, it says that the head of the tank is basically constant, meaning that the water level, this h, which, so it just means that this h is just a constant and is not a function of time. Okay. All right. So having said that, let's see what are the tools that we have now in our disposal for calculating this u naught. So the objective is you just need to calculate the magnitude of the outflow velocity, which is u naught. And then the outflow velocity have a profile something like this. Okay. So it becomes very clear that in order to calculate, so the problem demands, it says that there is a fluid coming in, there is a fluid going out, and there is a constant head that is maintained in the tank. There are two things that should just pop up in your mind once you see this kind of scenario. The first thing is that you must use something which is known as the conservation of mass, and you will use the conservation of mass through the Reynolds transport theorem. Okay, these are the two things. At least there should be there should be a bell that should ring into your mind when you see such kind of problem. See, it's very easy. I mean, even if it doesn't appear so trivial, you can at least appreciate that there is a fluid that is coming in, there is a fluid that is going out, so something has to be conserved. So what has to be conserved is that the mass of the fluid, or in other words, it's more correct to say that the mass of the fluid inside the control volume has to be conserved. So the first thing, you must look for mass conservation, and the most appropriate way in fluid dynamics for applying the mass conservation is the Reynolds transport theorem. Okay, so the first step what we will do is, as we have did many a times, is that we will choose a control volume which encompasses this the area of interest that we are supposed to take, or it's not area of interest, it's the volume of interest that we are supposed to take in this problem. So what we will do is, we will consider a control volume. Sorry. So we'll consider a control volume that basically take care of this region. Okay, so this is the control. So this is the first step that you need to do when you are applying mass conservation. And let's now do it. So what we will now do is, we will apply mass conservation using RTT. So what we saw is that, so by now I think you should be at least an expert of using RTT, because you have done this multiple times. So we will apply the mass conservation, which says that, if you remember, the left hand side was rate of change of mass inside the control mass system. Okay, this is what mass conservation says. If so, this is what RTT says basically. If we apply mass conservation in it, the right hand side, it says that it is the rate at which the property, which in this case is the mass, which changes with respect to time inside the control volume. So it just becomes del T of integral over the control volume, okay, rho dV, where dV is basically is a differential control volume, and this V is basically the total volume that we are considering inside the control volume, okay, and the net efflux. So the efflux term is nothing but the closed surface area, I mean the closed contour. I mean it's like, so this, I hope you are familiar with this symbol. It's like you are integrating over a surface which is closed. Basically, it's not an open surface, it's a closed surface. That is something that you need to realize. For instance, the closed surface here is basically this surface on which you are doing the integration, okay, and the integrand, as you know, is of course rho v dot n hat dA. So that's it. That's the first step that you need to do in these kind of problems. So you just apply mass conservation, you just apply RTT for mass conservation. That's it. Now, can you tell me what happens to this term uh, in this context? Can you tell me, is it a zero or a non-zero? So what is the rate of change of mass inside a control mass system? We discussed this many a times. So this has to be zero, right? Because this is a Lagrangian. See, this part is an Eulerian description, as you guys know. This is a control mass definition. It's a control system definition. Okay, and this is a control volume description. This is a control system description. And we saw multiple times that in a control system, mass is always conserved. Okay, energy can, there could be transit of energy inside a control mass system, but mass cannot. So mass cannot leave and enter inside a control mass system, which means that when you encounter this term, that the rate of change of mass inside a controlled mass system, this is always equals to 0. Okay, I hope this is clear. All right, can you tell me what happens to this term? Now I'm assuming that rho is constant. That's the second step. So I'm assuming that rho is constant, which means that rho will basically come out of the integral. So it just becomes rho times of del T of integral over the control volume dV plus, what is this? It is this times dot n hat d. And since we know that density of water is constant, I can basically bring density outside the integral, because I'm assuming that rho is constant, which now means that I just end up, and since the left hand side is equal to 0, okay, I just now end up getting del T of integral over v dv plus integral over the control surface v dot n hat d. All right, I hope this much is clear up to this point. Okay, now let's look at the individual terms, okay, such that you get certain clarity. So let's just look at this term. So this term says, so what is this? It just says that it is del T of integral over v dv. So it is basically, so what is this term saying? It is saying that how is the control volume essentially changing with time. That's what they're saying. So the only way that the control volume basically can change with time in this context is that the height of the tank should be a function of time. But this is not the case here. Remember, it was in the earlier case where the water level was constantly rising with time. But here, since your height is since you're maintaining a constant head by tuning the flow rates, okay, your control the your volume of the so the volume of the control volume is not a function of time here. I hope you can realize this context, because you can crudely write that that this can be written as del T of the area of the tank, okay, times h of t, which is nothing but the height of tank, which is basically this h. So okay, so they are just denoting this as h, so we'll just denote this as h. Okay, now area of the tank is just a constant because the tank is just a fixed volume, which means you can simply write this term as at times dh dt. Now in the earlier problem, dh was a function of time, but in this problem they have essentially said that this is a constant head tank, which means that h is not a function of time. And this is obvious, right? Because you are maintaining this water level by by a fluid that is coming in and by a fluid that is going out. Okay, so you are basically tuning the outlets to maintain a constant head inside the tank, which means that this term is essentially 0 because of the fact that you are maintaining. So so the reason is that a constant head is maintained. Okay, which means that this term basically goes to 0. That's it. So all we are remaining is that we just need to evaluate this term. That's it. So the RTT then boils down to the fact that integral of closed surface integral over the control surface v dot n hat dA is equals to 0. All right. Okay. So now how do we proceed? Is the question that should pop up into your mind. Okay. So we did all the simplifications that we had given the context of the problem and given the physical paradigm that we saw. The RTT just simplifies to the fact that the simplifies to the fact that this term basically equals to 0. But now how do we get u naught? Because the ultimate question is that we need to calculate this magnitude u naught, right? Which is the magnitude, you can say, you can interpret as the center line velocity of this varying velocity profile. This is something that, because the center line velocity is what you will obtain when y1 is basically equals to 0. Okay, and that is something that you need to calculate. So the bottom line is that how do you get this? Okay. So this is again similar to the things that we did, is that you need to now apply this, you need to now evaluate this at the control surfaces. So you can appreciate that in this control surface, there is only two areas through which fluid is coming in. One, this area, and the other is basically this area. Okay, so I'll call this as, as maybe A1, and I'll call this as maybe A2. I hope you realize and you understand what we are doing. Okay, so this integral and the rest, the rest of all the areas, for instance, this and this, there is no fluid that is coming in, there is no fluid that is going on, meaning that v is 0, which means that the integral, it is not necessary to evaluate the integral anywhere else apart from the areas A1 and A2. I hope this is clear. So this term just now boils down to integral over A1 v1 dot n hat dA plus integral over A2 v dot n hat dA, and this is equals to 0. All right. Now let's see what is basically happening at A1 and what is basically what is the change that is happening at A2, because of the fact that you have different velocity profiles now at A2 and you have a different velocity profile at A1. Okay, so let's treat these terms individually. Okay, so now if you evaluate this integral, what you basically have that your u, that is your velocity at section A1, is nothing but a uniform velocity, and the direction, the unit normal, is basically in this direction because there is a net flow inward inside the tank. Okay, which means that your u is basically u infinity, and the unit normal is what? The unit normal is n hat in this direction. The local unit normal is basically n hat. So your u is u infinity. So it is actually minus u infinity n hat, because your n hat is in the other direction and your fluid is basically coming inward inside the control volume. So it is actually minus u infinity n hat. Okay, I hope you understand this. See, this is very simple. I'm just making you understand that what is. So let's see the region that is coming inside the tank. So inside the tank, the region is something like this. Okay, I'm not drawing the full picture. I'm just drawing the region where the flow is coming inside the tank. Okay, so in this section, we have a constant velocity profile. Okay, and if I draw the velocity profile, it is basically, something like this. The magnitude is, so this is the velocity profile. The magnitude is u infinity. The direction is actually in the negative of n hat, because of the fact that your n hat is, so your normal always faces outward the area, then that's why your direction of n hat in this sense is this one, and that's why you got an u as minus u infinity dot n hat. I hope this is clear. Okay, so now if we now evaluate this integral now becomes, can you tell me now what does this integral become? I mean, just give it a try. because this is easy. If you can figure this out, the next step is to figure a more complicated version, because in this case, the velocity is not constant. We will see what is basically happening in section 2. So can you tell me what this integral basically then boils down to? And remember, this height, this distance is h. Yes, give it a try.
We have to substitute the value of area like
Yeah, exactly. So
b
what
into
does
h.
exactly? See, this integral now, yeah, you are absolutely right. So this integral now, it basically, so what does it become? It becomes a1, it is u infinity n hat dot n hat. Always follow the maths clearly. Okay, the math will lead you to the result. It's not and that's the reason why you should not skip the math. If you want to develop a good understanding of the physics that is happening in the problem. Okay, so if you substitute the velocity is minus u infinity n hat, and there is a dot product with n hat, so this becomes n hat dot n hat, and the dA is basic. So what is dA? dA is like you choose a y, okay, and in this y you take a differential area which is, let's say, dy times the width b. This is something that you can realize it as dA. Okay, which means your dA is like you can, so you, I hope you understand that your dA would basically be the width multiplied by dy. That's it. Because see, dA is the differential area through which the fluid is coming in. So what can be the differential area? So if you increase this in order to have a good understanding, I'll show you here. So you take a y, choose a small strip of y dy, and then you take the width in the lateral direction. So this basically is the area, and this is the area through which I hope the picture is clear. This is the area through which a differential fluid volume would basically pass through, and this area is nothing but b times dy, and that is typically your dA. I hope you understand this, and please let me know if I'm assuming that you understand it, because this is something that we have already done. But still, if there are any doubts, feel free to stop me and just let me know. But I hope this bit is clear. All right. So if you if you simplify this, so n hat dot n hat is just 1. The dot product of the unit normals are just 1. This just becomes u infinity integral over a1 b dy. But now, since it says that the width is constant, this surface integral can now be written as you are simply integrating from 0 to h. That's it. I hope this is clear. See, actually we are integrating on a differential patch of area, but the width is just constant, which means the variation only comes in the y direction, and in the y direction you need to integrate it from the point where the pipe from the point below the pipe to the section which is at the topmost version, the topmost position of the pipe, meaning that you just need to integrate it from 0 to h. And if you do this integral, it's just very simple, because your b is constant. You simply get minus u infinity b times h, where h is basically, as I said, is the height of this inflow section, which is nothing but this section. That is something that the problem has given to you. Okay. All right. I hope this is clear up to this point. So this integral simply boils down to minus u infinity b times h. Okay. Now let's evaluate the other integral. That is a little tricky, and I'll tell you why this is a little tricky. Okay. So the other integral is integral. So you're integrating over a2. Okay. V dot n hat dA. All right. So now let's clearly draw the outflow section of the pipe, meaning that I'm drawing. So what I'm doing is I'm drawing this portion. Okay, and let's see what is happening. So so I'll draw this. Please bear with me. Uh, so this you can think of as the outflow section, and in this outflow section you have a velocity in this outflow section you have a velocity profile which is something like this. Okay, the direction in this, the unit normal in this direction, they have called it as n1 hat, which is again the local unit normal in this direction, and this width is similar, and in fact it is not the width, sorry, the height, or you can say the length of this section is similar. In fact, it is exactly equal to h, which is the length of the inlet section of the pipe. Okay. I hope you are with me on this point. So what they said is that this velocity profile they have given to us, this velocity profile u bar is u naught in u naught into 1 minus of y1 square by h square, and since velocity is a vector, its direction is in in the same direction as n1 hat, where this y1 is essentially the local y coordinate, okay, at this section. So this is basically y1. I hope you are clear and on this aspect. Okay, please let me know if you have any doubts regarding this. So this is the scenario. This is something this is something that they have given. Remember, I again say this time the velocity is positive because the direction of the velocity and the direction of the unit normal are basically the same. Okay. So then let's calculate this v dot n hat dA for this given outlet section of the pipe. So remember, I'm drawing this. So this is basically the outlet of the pipe. The only difference that you can see here is that with respect to the inlet section, as I have said it repeatedly, is that the velocity profile, instead of it being just a constant, it is actually a parabolic profile, which is a more realistic scenario of what actually happens inside flow through pipes. Basically, you will so in a viscous fluid, if the fluid is viscous, you don't encounter uniform flows typically, because you get something which is on the no slip boundary condition at the walls. So because of the essence of, or because of the presence of viscosity, okay, you tend to see a parabolic profile of this form. Okay, I hope this is clear. All right, so let's now evaluate this. So if we evaluate this, and of course let's also see what would be the dA, that is the differential area. Again, the differential area would just be same. What you need to do is you need to choose a y at any given one, or I would say y1, because the local y coordinate here is y1. So at y1, you need to choose a differential, dy1. Okay, and of course there should be a width. The width you can assume it to be going like inside this direction. So for this dy1, let's do it. So for this dy1, this is basically the width. So your area is going to be something like this. So this is your b. I hope this is clear. And this is your dy1, and this is essentially the differential area through which you are basically assuming that fluid volume would pass through, and then you will basically integrate it from this point. You just need to integrate it from here to here. That's it. So your dA, I hope this is clear. Okay, and please let me know. I'll stop and repeat, like, if there are any confusion. So your dA here in this case is simply going to be v times dy, which is exactly the same as it was before. Okay, all right, so let's do this integration. So then this integration becomes 0 to h. Sorry, now it will not become from 0 to h, because in this case you have chosen the axis to be at the center line of the channel, meaning that you now need to integrate from here to here basically. All right, so your integration will now become, I hope you understand, it will now become from minus h by 2 to plus h by 2. Why? Because your axis is now here. Okay, that is again something that is given in the problem. If you choose your axis here, you need to integrate it from 0 to h, because you can see that your problem has said that your axis is basically here, that is in the center line of the channel, and that's why I'm integrating it from minus h by 2 to h by 2. I hope, yeah, this thing is clear to you. Okay, all right. So then so what I'm doing is, I'm evaluating this integral. So this integral is just minus h by 2 to h by 2. Okay, you are integrating with respect to dy. Okay, and then you need to evaluate this v dot n hat. Now you can very nicely say that your v dot, actually this is n hat 1, because the unit normal vector locally in that direction is n1. That is something that they have given to us, which is basically this. So you can easily now appreciate that your v dot n hat is just going to be this term, u naught into 1 minus y1 square by h, because this n hat and this n hat of the dot product will just give you 1. Okay, which means this will just now become u naught into 1 minus of y1 square by h square, okay? And there is a b term here because of the width. Is it clear or not? Like, is this thing clear or not, what I have written?
Yes,
All right,
it's clear.
yeah, good. So now that's it. That's all that we need to do. From here, we just need to integrate, and this u naught will basically come out because it's a constant actually. Okay, so I'll write this term. So this u naught and the width is a constant because the width of the tank they're saying it's just a constant. And of course, the width cannot be a function of y because the width is in anyway it's in the other dimension with respect to y. Okay, so this u naught times v, it is an integral from minus h by 2 to h by 2 1 minus y1 square by h square. This is y1 actually. This is dy1. That's it. So now what I will do is I'll just combine this term, meaning I'll just combine this term and this term, which is essentially this and this. That's it. So combining the terms. So what I get is the first term is just minus of u infinity bh. It is just minus of u infinity bh plus the second term is u naught b integral from minus h by 2 to h by 2, okay, 1 minus of y1 square by h square dy1, and this is 0. Now couple of things very nicely get simplified. One, the fact that this b and b will just get cancelled out, and and what, so basically what you get is you just get u infinity, just bring the other term to the other side, so you get u infinity times h is nothing but u naught into integral from minus h by 2 to h by 2 1 minus of y1 square by h square dy1. Okay, which means that your u naught, the thing that you need to calculate, is nothing but u infinity times h by integral from minus h by 2 to h by 2 1 minus y1 square by h square dy1. Okay, all right, so let's evaluate this integral. That's the last part that we need to do. This is essentially, so if they ask you the analytical form, this is basically the analytical form, but now they are asking you the answer. So let's evaluate the integral. Okay, so let's evaluate this integral. So what this integral would be, I can just write down this integral as, see, this is an even function, this is also an even function. Okay, so I can very nicely write down this integral as integral 2 times of, I hope you know this property of integration for even functions, basically that it becomes 2 times of 0 to h by 2. The first term would just be integral of dy1 minus integral of 0 to h by 2 1 minus of y1 square by h square dy1, and then there's a bracket because of the 2. I hope you know what I'm doing here. Okay, all right, so the first term would give me what? The first term would just give me h by 2. The second term would just give me what? From here, sorry, I think so what did I do? This is just so one is taken account in here, and this term is basically this. Okay, all right, yeah, that's it. So the first term, from the first term you just get an h by 2. From this term you get what? So 1 by h square will just come out. This would become y1 cube by 3. Okay, this integral would become y1 cube by 3, and then you need to substitute and you need to evaluate this from 0 to h by 2 basically. Okay, so this becomes 2, and then this is h by 2 minus 1 by h square, 3h square basically because there is a 3, and y1 cube, so this would be h cube by 8. I hope you understand what I'm doing. Okay, just this, that's just the integration, that's it. So this now becomes h minus what this would be. So this becomes, so there's this 2, and this 2 will cancel, and from here you will basically get a 4 which means it becomes h minus h by 12, because this h square and h cube will just leave one h. I hope you are clear with this point, okay? This just becomes 11 by 12 h. So that's it. This integral, this whole integral, this whole, integral is just this term, 11 by 12 h. That's it. So that's it, guys. Just substitute this value. So your u naught is u infinity times h, by the integral is just 11 by 12 h. Okay, and I think in your question, your u infinity, if you remember, your u infinity is just 11 meter per second, which means if you substitute this as, this means that your u infinity is 11. Okay, just substitute this. So this is, so this h and h would cancel. This is 11 by 11 by 12. So your u naught is nothing but 12 meter per second. That's it. That's the answer. So u naught is 12 meter per second. In your assignment, the accepted range of u naught that for which you will get marks, if I correctly remember, is between 10 to 15. So you should, so if you are doing the math correctly, you should exactly get 12 meter per second. But if there is still some anomaly, even if your answer lies between 11 and 15, you would still get the marks. That's the thing. So any questions? Is it clear how this answer came out? So the exact, yeah,
Yeah, it's accurately clear, sir. Thank you, sir. Thank you so
okay,
much.
yeah. All right. There is one more question. I'll discuss that and then I'll proceed. I believe you asked just one more question, right? I think that is the question number 8 that you asked.
Yes, sir.
Yeah, exactly. That is a little. I mean, it's a better question, I would say. I mean, it's a good question, and we will discuss that. But I'll stop here for some time. If you have any doubts, you can ask, or else we'll proceed. So I hope the thing is clear. Like how do we did this sum, and how did we end up getting the answer basically. All right. Okay, I'll stop here for a couple of minutes, and then we'll proceed with the next question. Okay. So what this you know what this question says so it's something interesting. What it says is that there is a spherical tank, and you are basically filling air in that tank. Okay, I mean, you are not filling. So at a given pressure and initial temperature, at a given initial pressure and an initial temperature, there is air in that particular rigid spherical tank. The initial pressure and the initial temperature are given to you. So Pi, I will call it as the initial pressure at time t equal to 0, is basically given to you as 400 kilopascal, and your initial temperature, I will call it as Ti at time t equal to 0, is given as it is also given as 400 Kelvin. All right. Now what you are doing is, from this, in this spherical tank, let's think that there is some leakage that gets developed. Okay, let's say that it's a spherical valve, and there is some knot that is that so there, I mean, there are some fittings, and you are basically joining the seats of the tank with some what do they say, with some, I don't know. Maybe with some joints, and through these joints, let's say there is some leakage of air that is being taking place, and because of which, since the air is at a greater pressure inside with respect to, let's say, the ambient, okay, and because there is a pressure difference, the air basically moves out of the tank. Okay, so it just says that compressed air exhausts a small hole, okay, in a rigid spherical tank. The diameter is given. Initial pressure and temperature, as I already said. The initial mass flow rate of the exhaust air is given to be equal to 0.02 kg per second. That means that at time t equal to 0, you know the rate at which the air is coming out. What they have specifically asked is, what is the time required such that the density of air inside the tank drops to 40%. This is all that they have asked. Okay, seemingly, you may say that this typically looks like a thermodynamics problem. Yes, indeed, it's kind of a thermodynamics problem. But what we will do is I'll show you by using RTT that how nicely and how very formally you can basically find out the answer of this problem. But I hope the given problem is clear. So it just says that you had air inside a tank at the given initial pressure and initial temperature. There is a small hole. This hole may develop because of manufacturing defects and of any several other physical regions. But the fact is, since there is this hole, there is a leakage of air. The initial mass flow rate of air, that is, I would call it as m dot I. Okay, uh, m dot I is given to be equal to 0.02 kg per second. Okay, now given this, they have asked you is that how much time it will take for the density to drop to 40%, meaning that they're asking rho by, I would say, the initial density to be rho I equal to 0.6. For this to happen, how much time will it take? That's it. That is what they're asking. Because if the density fall by 40%, the density at that time would be just 0.6 times the initial density. Okay, and from there I got this at 0.6. Just give it thought and you will understand why did I basically wrote this. Okay. So what they're asking is they are just asking how much is the time required for this. That's it. All right. So what we will do is we will again start off with our basic control volume approach. So let's draw the tank first. So there is this spherical tank, and let's say there is a small hole inside this tank. I'm just exaggerating it, but you can think of this hole to be a very minute hole with respect to the size of the tank. So since there is a hole, there is a leakage of air that is coming out through this hole. Okay, now you must understand that since it is air. Okay, when air basically moves out of this tank, the pressure inside the tank would basically drop, meaning that the pressure would basically decrease with function of time. That is typically because air is just moving outside the tank, which means that the initial pressure of 400 kilopascal would now drop. And because of this drop in pressure, since the volume is constant, you know that there would be a drop in density. Okay, and this is typically the reason why density will basically decrease when the air moves out. And the mass flow rate and you also need to understand that the mass flow rate at which the air moves out is also not a constant, and it will inevitably be a function of time. You can understand it something like this. Let's say you are filling a balloon. The balloon is not a control. So the only difference between balloon and this problem is that the volume of the balloon would also change. But here, let's say you are basically filling up some kind of a rigid balloon, and then through some opening you are allowing the air to basically pass through, which means that at initial time air would basically move faster. Okay, and then when there's a less chunk or a less volume of air that is left, the mass flow rate of air would also consequently decrease as and when time progresses. Which all I want to now say is that the mass flow rate will also be a function of time, just like how the pressure and density is. This is something that you need to understand. So the mass flow rate at all time will not be a constant here, because of the fact that you are now seeing at least a transient problem in this scenario. I hope this is clear. And please stop me if you have questions at least to this point of time. I hope you understand this. Okay. All right. Okay. So this is the tank, and this is through which your air is basically moving it. I'll consider the mass flow rate as m dot. This m dot in general would be a function of time. Okay. You had so what you had air filled in inside this tank. Okay. And all you need to know is that you just need, as I said, you just require the time when your density drops by 40%. meaning that you just require T when when the ratio of rho by rho I, this rho is, you must realize that this is a function of time. So the ratio of rho by rho I, when it becomes 0.6, you just need to evaluate the time. That's it. So let's start off. So the thing is, we'll still apply RTT and we will still apply mass conservation, but we will see that how powerful RTT is in this regard as well. Okay. Uh, so the first come first. So what we will do is let's draw the control volume. So our control volume would be something like this. Okay, this is my control volume, and as you can see, this is the area through which your air is basically escaping out. Okay, so straight here I'm writing the mass conservation. This time I'll not explain much because we have seen this many a time. So the left hand side is just going to be equal to 0. I hope you understand this. Okay, the right hand side is going to be del del T of integral over the control volume rho dV plus integral over the control surface rho v dot n hat dA. This is just we are applying RTT. I hope at least by now you know like this from how you know how this thing come. So you're applying RTT for mass conservation. Okay. Now we will do one very important assumption. We will assume that your density of air, the density of air, this is not varying. Please listen to this carefully. Okay, we'll assume that the density of air is not varying spatially within the within the tank, meaning that the only way density can vary is with time. It cannot. So I'm assuming that the dense so the air is kind of homogeneous. Okay, meaning that my density inside at it is just it can be like that. The density of air inside any position of the tank is just the same. It is just that your density is just a function of time. And this is also because of the case because air is escaping outside the control volume, to be precise. Which means I can bring this density outside here. But remember, I cannot bring density outside this derivative. Why? Because since my air is now escaping, the density of air is in general and will inevitably be a function of time, which means that I cannot assume that the density is constant. And this is the essential difference between liquids and gases. Actually, I mean, for liquids you can crudely say that your density is constant even if you have fluid going in, fluid going out. That's a crude approximation we do, but for gases you cannot basically do this. Okay. uh, so you understand what I'm saying is that I'll assume that my density is not spatially varying inside the control volume, meaning is that I can bring this outside the volume integral, but my density is a function of time. You should understand this, which means so I cannot bring this density directly outside this derivative. I'm bringing it outside the integral, but I cannot bring it outside the derivative. That is something that you must understand. Okay, so this now just becomes del t of rho integral over v dv, okay, plus the closed surface. So this is actually the closed surface integral, okay, over the control surface rho v dot n hat dA. All right, now take a close look at this term. This term is what? You pick any differential volume inside this tank, and you are just integrating the differential volume throughout the volume of the tank. And remember, this is a rigid tank. So the volume of the tank cannot be a function of time. Okay? Which means this term, this integral of the differential volume, integrating it over the entire volume is nothing but your V tank, that is the volume of the tank. And since your tank, so that is where essentially the difference lies between a rigid tank and a balloon. If had this been a balloon, this term will also be a function of time and you cannot take this outside the integral. But since this is a rigid tank, your volume is constant, so you can take this V tank outside this integral, which means this term now just simplifies to 0 equal to V tank d rho by dt plus integral over the control surface rho v dot n hat t. I hope you are with me so far. Is this clear or not up to this point?
Yes, sir.
Yeah, exactly. Do you realize
Yes.
the difference that had this been a balloon kind of surface, you cannot basically calculate. I mean, take this outside. You cannot take the volume outside the integral because your volume also will change with time because of the flexible area. But now since your tank is a rigid spherical tank, that's what they have said, which means that even if air is going out, this will be manifested by a drop in density and a drop in pressure, but the volume will just be the same. Okay. And also, a drop in these quantities will also result in a drop in mass flow rate. We'll also basically see this. All right. Okay. Now, this term is now a kind of well settled term. Okay. I have the volume of tank. I know what is the volume of tank. Okay. This is just 4 by 3 pi r cube because it's a spherical tank. We know the diameter. So this term is just a known term. Okay. This is just a known quantity because this is 4 by 3 pi r cube. You know the diameter of the tank. This means you know this term outrightly. Okay, I don't know. I understand my density is a function of time, so this is just a derivative that I have. But what is this term? How do I take care of this term? Because this term contains velocity, but nowhere I don't know what is the velocity field of air. Okay, but this is where we need to be little bit careful, and we need to observe things here. Okay, so what does this term? So typically, what does this term mean? This term, so you realize that what is the dimension of this? I mean, not dimension. What is essentially the physical quantity that this term reflects? It is density multiplied by velocity and an area. So is it not a kind of mass flow rate that essentially that essentially we are discussing? So precisely, this term is known as the efflux term, and efflux is nothing but the net mass flow rate that is going outside the control volume. And now in this scenario, we don't have anything that is coming inside, which means the efflux is nothing but the mass flow rate of air that is going outside the control volume. That's it. So this term can now be written as this. This term it is just m dot as a function of time. That's it. Or I would more specifically say it is the exit mass flow rate of air that is going out. Again, I will repeat, if you look at the physical quantity, this physical quantity is nothing but mass flow rate because it has got density, it has got velocity, and it has got air. Because I don't know the velocity field, I don't have the power to basically specifically evaluate to evaluate this integral. So what I will do is I'll try to see what this integral physically means, and in this context, because there is just a outflow without any inflow, it is just the mass flow rate of air that is leaking from the rigid tank. Okay, which means this is just 0, and this is V tank times d rho of time by dt plus m dot e. That's it. Okay. I hope you are with me on this so far. Please let me know if you have any doubts on this. Okay. All right. See, the idea again is, so you must also think at the back of your head that what you are essentially evaluating. You are essentially you are evaluating this term to be precise. Once you know how your density varies with time, you give me any time, or you give me any value of density, I will give you the time. You give me after 100 seconds what will be the density. If you ask me after 100 seconds, okay, what will be my density, I'll ask you, give me the time, I'll give you the density. Or in the other way around, if you ask me that how much time will it take for the density to drop to 40%, as what the question is asked, okay, then you just give me the value of the density, I'll give you how much time it will take. Which means all you need to know is you just need to have you just need to calculate what will be, how does your density effectively varies with time. That's all that you are trying to calculate. Okay, now there is still a challenge that is left. How do I basically now evaluate this mass flow rate? Because I said that this mass flow rate, okay, it is not constant. You cannot write that this is equal to m dot I. No, that is not right. It's just a no. That is typically because since your pressure and your density is varying, the mass flow rate of air that will leave the tank will not be equal to the initial mass flow rate. That is something that you cannot do. So then how do you evaluate this? So all I am saying is that this is nothing but m dot e as a function of time. So here is something. So in this case, so this is the most important part of the problem. You need to consider, I won't say it's an assumption, but you need to, think about it physically. You can say that your mass flow rate of air, okay, that is leaving the tank is essentially proportional to the density of air. That is of course inside the tank, which means that if you have air at a higher density, you will have a greater mass flow rate. As and when the density of air drops, your mass flow rate will also drop. Okay, this is one of the most important thing of this problem that you know need to understand. And once you understand this, that's all, your problem is solved. Okay, see, this is a realistic scenario, right? You just fill a tank with air. Okay, your mass, you will see that your mass flow rate, of air that is coming out from the tank in the transient zone, of course, is a function of what is the density of air that is inside the tank. You have a higher density of air, you will see that your air is basically coming out faster. Not faster, faster is not the correct word. You will see that a more, volume of air is coming out, or not volume, I mean a more mass of air per time, per unit time, the mass of air that is coming out is more. When you have a lesser density, the mass of air that is coming out per unit time also diminishes. So this means you can say that your mass flow rate of air as a function of time is proportional to your density of air that is present inside the tank as a function of time. That's it. So once you consider this, in order to remove the proportionality sign, you can just say that your m dot e, that is your exit mass flow rate, is some lambda, okay, which is the proportionality constant. Lambda is nothing else, it's just a proportionality constant, rho of t, where lambda is just the proportionality constant. All right, so that's it. We will just substitute this here. But remember, we also need to calculate lambda, but we will see how. So we'll have a very nice way of calculating lambda. But first come first, let's substitute this thing into this expression. So we have what? So what do we have? We have v tank times of d rho by dt plus lambda times rho, which is a function of time, of course, is equals to 0. Okay. So this is basically the differential equation that governs how, your density essentially varies with time. Okay, can you tell me, is it a linear ODE or a non-linear ODE? First of all, you need to understand that this is an ordinary differential equation because your density is just a function of time. Okay, is it a linear or a non-linear? I'm just asking. Solving is a different thing, but you need to also develop a little bit good, understanding of the system that you are currently dealing with. Okay, so the question is it a linear ODE or a non-linear ODE, or the next question is it a homogeneous or a non-homogeneous, differential equation? Can you give it a try?
I think it's a linear.
Yeah, exactly, it's a linear because your unknown variable is rho, and nowhere, you have another rho or a derivative of rho multiplied with the unknown variable. Okay, or you don't have something, terms like rho square, which means this is a linear ODE. Is it a homogeneous or a non-homogeneous? Yes, you are right, it's a linear ODE. Is it homogeneous or is it non-homogeneous? See, the definition of homogeneous and a non-homogeneous system is that, yeah, go on. I mean, you have some answer.
I think it's homogeneous.
Exactly, it's homogeneous. It's homogeneous because rho equal to 0 essentially satisfies this system. Okay, but we are not seeking trivial solutions, because rho equal to 0 is known as trivial solution in the literature of mathematics. But we are not, so rho equal to 0 is not the solution. Okay, because if rho is basically equal to 0, then your density is 0. I mean, that's not the realistic solution we are looking for. Okay, so It's a linear system and it's a homogeneous system. That's all that you can say. Okay. But anyways, just let's go ahead and find this. So this becomes d rho by dt, and then this becomes what? It just becomes minus lambda by the volume of tank times rho. So there is something which is known as, variable separation. We have done a similar problem of this sort. So we'll just separate the variables, d rho by rho, and this is minus lambda by v tank times dt. That's it. Let's integrate it now. See, at time t equal to 0, I know I have an initial density of rho I. I can calculate rho I because I have the pressure and temperature. Okay, if I have the pressure and temperature, I know what is my initial densities, which means that at time t equal to 0, this is known. At time t equal to t, I just require what is rho of t. Okay, so if you evaluate, you will, very nicely get an expression of something like this. So it is rho by rho I. You just do the integration. That's it. So from this you will get a ln of rho. If you evaluate the limit from rho I to rho t, you'll basically get ln of rho minus ln of rho I, and from here you'll just get ln of rho by rho I. And if you take the ln to the other side, you'll basically get an exponential term here. I'm just skipping the test. I'm skipping the steps here because this is just the math, and we have done this thing many a times. Okay, in these discussion sessions and also in the lecture series. Okay, so you just do this integration, substitute the integration limits. You will just see that your rho by rho I is exponent of minus lambda by v tank times t. This is typically, you realize that this is typically how your density essentially varies as a function of time, and you can see that this is an exponentially decaying function. I hope you realize that, which means that your rho as a function of time, okay, is nothing but your rho I, which is the initial density, times exponent of minus lambda by v tank times t. All right. Now we don't know one thing that is still left to figure out. Okay, we don't know what is this lambda. But before calculating lambda, I'll show you how do you basically calculate lambda. But before calculating lambda, let's calculate the known quantities. We can calculate rho I, right? Because if I apply the ideal gas, okay, if I apply the ideal gas as I mean the ideal gas equation at t equal to 0, that is for the initial condition, I can just write that pi is equal to rho I times r ti, where r is just the characteristic gas constant for air. You know it has got a value of 2.87 into kilojoule per kg Kelvin. Okay, which means that your rho I is just pi by rti, and you just substitute the values. Your pi, it is given that your pi is 400 kilopascal. Okay, your r is 0.287 kilojoule per kg Kelvin. So kilopascal and kilojoule, the 10 to the power 3 terms would just get cancelled. So this term is just 2.87 into your ti is 400 Kelvin, which means that your initial density rho I is just so I have the answer here. I'll just you do the math, just do this calculation. Your initial density should come out with 3.48 kg per meter cube, which means I now know this. This is sorted. All I now need to know is lambda. That is also very simple. Why? Because I know that the relationship between lambda and mass flow rate and the density is this, which means I can use this relation at time t equal to 0, that is the initial condition, because I know what is the initial mass flow rate. I know the initial density, that is something that I just now calculated, and then this will give me lambda, and that's it. Because lambda is a proportionality constant, it cannot vary with time. Okay, these two things will vary with time. Your proportionality constant won't vary with time, basically. Which means it is given in the question that your MI, the initial mass flow rate, what is the initial mass flow rate? This is the initial mass flow rate, 0.02 kg. Okay, so I can use the fact that my MI is basically equal to lambda times rho I, which means I can write that my lambda is the initial mass flow rate by the initial density. The initial mass flow rate is 0.02. Okay, it is in kg, and your rho I is basically 3.48, which means so your lambda has got, so if you just evaluate this, I have done this a priori, so your lambda should come out to be equal to something like 5.47. Just do the math just from your end. This is just into 10 to the minus 3. See, you can understand this. This m, the mass flow rate, has got a unit of kg per second. This density has got a unit of meter cube per second, which means your lambda should have a unit of, uh, I hope I'm clear. Sorry, so your lambda, I mean, effectively your lambda will have a unit of, if I'm not wrong, your lambda will have a unit of meter cube per second. That is typically because, your mass flow rate has got a unit of kg per second. Density has got a unit of, what is density? It's mass per unit volume, which means it is kg per meter cube, which means your kg will just get cancel out and your unit of lambda is just meter cube per second. But that's it. That's your lambda. So that's it, guys. You have evaluated rho I, you have evaluated lambda. Just substitute it here, and you know how essentially your density uh, pinpointedly basically varies with time, and that's all that you required. Okay, so you know that now your rho I, that your rho is rho I. Rho I is just 3.48. So this is 3.48 into exponent of minus lambda. Your lambda is minus 5.47 into 10 to the power minus 3 by volume of the tank. Volume of the tank is 4 by 3 pi r cube. That's it. So 4 by 3 pi r of the tank cube, okay, where you know the diameter of the tank, meaning this term is known, times t. That's it. Where this term, this term is also evaluated. This term basically comes out to be 0.113 meter cube. I'm not doing the math again because this is just trivial, just showing you how this algorithm, I mean, this step is done basically. So it is 3.48 exponent of, it just comes out to be, minus 5.7. Please, verify the algebra at your end. I mean, this you should be, able to do this at this point of time. It's just 0.113, and then we have this time. So that's all. That is just what your question is asking. Because so what you now require is, they're asking you that what is this basically, rho by rho I equal to 0.4, and rho I is, so rho I is just 3.48, meaning that you just need to substitute your rho as, or what you can do is you can bring this, you can basically, bring this term here, then it just becomes, rho by rho I. Okay, just don't need this term, and then you just substitute this term as 0.4 to be precise. That is what your question is asking. Okay, substitute this as, I hope you understand what I'm doing.
Uh,
Substitute this as
yes.
0.4. Yeah, go ahead.
Sir, is this
Yeah,
rho by rho I is 0.4 or 0.6?
yeah, that is something that you understand, that you need to understand. So what they're saying is that time required for the tank density to drop by 40%. By 40%, by 40% mean initially it was 100%. Your density has now dropped by 40%, meaning that your current value of density is zero point 0.6. Basically, you have a 60% density with respect to the initial density. Understand that, right?
Yeah, okay.
That's why this becomes rho by rho I as zero point 0.6, meaning that your current density is equal to zero point 0.6 times the initial density. You understand this? This is say drop by 40%, not drop to 40%. Had this been be dropped to 40%, then your rho by rho I would be 0.4. Okay.
Yeah, okay. No, no, no. In the last step, you mentioned the 0.4. Is,
Okay. Sorry. Okay. That's 0.6. Sorry. This is 0.6. Yes. Thank you very much. This is 0.6. Okay. And then this is equal to exponent of, this term minus 5.4 into 10 to the power minus 3 by 0.113 times t. So this is just the one variable, that t that you need to evaluate. Just equate, these two things, and you should get the value of time. I have the answer. You should get your time to be around 10 seconds, which means that you just require 10 seconds given these initial conditions, to for your density to drop to, drop by 40%. That is when your density becomes 0.6 times the initial density. That's the answer. So I understand this is more of an involved problem, but it's a good problem on RTT, because it shows that how vast the the usefulness of the Reynolds transport theorem and the mass conservation can be actually. Okay, any questions on this so far?
No, sir. Thank you so
Yeah,
much.
yeah, exactly. Yeah. All right. So we have spent a fair amount of time, but I think this was required because this is precisely why we have this kind of sessions. And once again, I thank you for asking this doubt. Please feel to ask further doubts, and we will happy to clarify. So what we'll now do is, if there is no other questions, because we have some time with us, we will start off with what I just now stated as axisymmetric flows, and we'll just stop here for a couple of minutes, and after that we will basically understand what axisymmetric flows are, and you know what is an axisymmetric flow typically because you have already seen this week's lecture. But we'll solve a problem. It's more, I understand this. So the problem that we do in this discussion session is an extended version of the problem that you get. So once you understand these problems, by knowing how the procedure is done, you should be in a good position to solve problems in the assignments. And even if if you have any doubts, you can always feel free to revert back to me. Okay, that's the idea basically. So we'll understand this axisymmetric flow by solving a problem. I call this problem as fluid dynamics of an extrusion process. I'll explain to you how this problem basically is, but essentially this is an axisymmetric problem, and you will see that the the simpler problem that you saw in this week's lecture series is essentially a part of this problem only. This is a more complex problem, I would say. Not so complex, but I would say it's kind of a two-dimensional problem. Uh, and we will see. So we may not finish this problem, but we will give a start and let's see how far we can go. But before that, I'll just fill my mug with some water. If you have any doubts, you can ask. I'll just be here in just 2 minutes. All right. Uh, Sorry for the interruption. So I hope there are no questions till now. So let's understand uh, what this problem is saying basically. So as we know, we are trying to solve at least as we saw in the previous week, we are trying to get analytical solutions to the Navier-Stokes equation. And as I said that outrightly solving the full Navier-Stokes equation is next to impossible at least at this point of time. Although you can solve this using commercial software, I'm saying that deriving analytical closed form solutions to the Navier-Stokes equation is it's still next to impossible. But if you make certain simplifying assumptions, then analytical solutions are possible to the Navier-Stokes equation. And one kind of solutions that we saw is for planar flows. For instance, we saw the Couette flow, we saw the plane Poisson flow, and then we solved the problem involving these two things. And we also looked into the concept of something which is known as linearity. It just says that if your governing equations are linear, you can basically superimpose the solution of simpler problems to basically get the solution of a problem which involves the two I would say which involve the two simpler problems basically. Okay, today we will do a similar kind of thing, but this time for an axisymmetric problem. It's so as I said, the name says that we will look into the fluid dynamics of something which is known as an extrusion process. I hope at least if you have studied manufacturing science, you know what is an extrusion process. I don't need to explain that any further. But we'll not see the the nuances of extrusion, but we'll see that what is the fluid dynamics that can take place in kind of in such kind of processes precisely. So what I have is I have two cylinders, as you can see. This is one cylinder of some radius A. This is another cylinder, okay, of another radius B. Of course, B is greater than A, as you can see from the figure. And these two cylinders are rotating with individual rotational velocities omega 2 and omega 1. Okay, it's just that there are two concentric cylinders. We call this as annulus. So these two cylinders are rotating with different angular velocity, and we have a fluid. Okay, we have a fluid that is basically filled inside these two cylinders, which means that if the two cylinder rotates, the fluid will also suffer rotation because of the fact that there is a viscosity. It's a viscous fluid. Okay, now typically in extrusion process, what they do is they give the molten materials kind of things. Okay, and then you kind of require an axial pressure to basically move the material outside. Okay, or to move the fluid outside in some sort. Okay, which means that apart from the rotation that is being taking place in the theta direction, we also have an axial pressure gradient in the z direction, where this is basically my z direction. Okay, so I hope you can understand the problem. The cylinders are basically rotating in the theta direction, which means that the fluid will also have a rotational velocity u theta in the theta direction. And I also apply an axial pressure gradient basically to move the fluid out, because this is so in extrusion. Once your product is made, you need to move the product out such that you have space for the next batch to be made. So for that you apply a pressure gradient in order to move this out. So I know this doesn't resemble a physical extrusion process, but crudely this is how the fluid dynamics is governed in these kind of scenarios. Okay, so this is the physical paradigm that we have. I hope this is clear. What they asked us is that in this case, you just need to evaluate the velocity field of the fluid that is basically suffering this kind of motion. That's all that you need to do. And they have asked us to consider certain assumptions. You need to consider your problem to be steady. You need to consider your problem to be fully developed, and more importantly, you need to invoke the assumption of axisymmetry. Okay, and I hope you have realized by at least by the end of I mean seeing the discussions of this week, that axisymmetry in cylindrical coordinate means, at least in cylindrical coordinate, means that your variables are independent of the theta direction. Okay, meaning that even if you, let's say, have a new theta, it can at max be a function of r, it can be a function of z, but it will not be a function of theta. Okay, that is the meaning of axisymmetry, meaning that you take a z axis and you just walk around the z axis. Okay, your variables will be independent of any polar locations that you stand around the z-axis, meaning that if I am here, let's say this pencil is my z-axis. If I am here, my velocity is let's say 10 meter per second in some direction. If I come here, let's say below the pencil, my velocity is still 10 meter per second, meaning that if I move around the z-axis, which is basically my pencil here, my variables are invariant. It's kind of like that, and this is the definition of axisymmetry in curvilinear coordinates, to be precise. Okay, we also have axisymmetry in spherical coordinate. We will not see spherical coordinate at this point of time, but later on there is something which is known as creeping flows, where we'll see solutions to flows past objects like sphere, and there I will convince you what axisymmetry means in spherical coordinates. But here, at least in cylindrical coordinate, axisymmetry means that your variables are independent of this theta direction. That's it. Having said that, in this problem, again, the objective is to evaluate the velocity field, but you now need to realize that since there is a rotation here, you will have a non-zero u theta component, and since there is a movement, there is a pressure gradient applied in the z direction, you will have a non-zero uz component. Okay, and since this is axisymmetric, your u theta and uz, okay, this will at max be a function of your radius and at max be a function of z. But they have also stated that your problem is fully developed, meaning that your variables u theta and uz, this will just be a function of r. And just try to convince yourself that you will not have an ur component of velocity. Think about it, why you will not have an ur component of velocity. Can you give an answer to it? why you will not have an UR component of velocity in this case? All right, we will see actually why we cannot have an UR component of velocity. Okay, so let's start the problem. I hope you understand that the objective is to evaluate the velocity field. So we will start the problem again very slowly. So we'll always begin such kind of problems. So remember, for problems involving calculating fields like solving the Navier-Stokes equation, always start off by writing the assumptions. Okay, so we'll start off again by writing the assumptions. Okay. So although they have stated, we will again write it down. So what they said is that we have a steady flow, okay, which means that your variables are independent of time. I hope you understand that. Then I have an axisymmetric. I'll just write it as in the short form. So I have an axisymmetric flow, and I said that this means that your variables are just not functions of theta, okay. And the other assumptions are that we will not consider any body forces, so no body forces. And again, another important assumption is that it's a fully developed flow. So if you understand, whenever, as I said in the beginning of this class, is that whenever there is a fluid that is flowing through a pipe, okay, initially at up to a certain length, there is a region where the flow is developing, and after that region only you attain the condition of fully developed flow. So we are considering the pipe length to be such large, and we are in the zone such that we are neglecting these developing effects, okay, because developing effects are very difficult to analyze analytically, okay. So we will neglect this effect, and we'll consider a region inside the pipe where the flow is fully developed, meaning that your flow properties are not a function of z. Okay, I hope you understand that. So the fully developed condition, of course, I think you know this, that your flow properties will not be a function of z, and there's something, so there's a more, I would say there's a more, what to say, a more general term that is used. This is something known as the translational invariance, typically, that you stand at any location inside the pipe in the developed region, you will see the flow field to be exactly same. Okay. All right. So these are the assumptions, and I stated the consequences of these assumptions. I hope this is clear. So next, what do we do? Once we write the assumptions, we start off by writing the continuity equation first. Okay. So let's do this. So let's start off with the continuity. So the continuity equation in cylindrical coordinate is something like this. I have 1 by r del r of r ur plus 1 by r. You just pick any standard books. You'll just see that you will get the continuity equation in different coordinate systems. This, of course, we'll use in cylindrical coordinate system because the geometry expects us to basically use a cylindrical coordinate system because it's a pipe flow. There is this z direction, and then we have the radius and all those things. So we'll be sticking to the cylindrical coordinate system. I hope this is clear to you why we are in the cylindrical uh, frame of reference. Okay. So the first term is 1 by r del r of r ur, and the second term is 1 by r del u theta by del theta plus the next term is del uz by del z, and this is equal to 0, where your ur, u theta, and uz, these are the three components of velocity in the velocity field in the cylindrical space. Okay. All right. Now can you tell me, based on the assumptions, which are the terms that straightforward goes to be equals to 0? Can you tell me?
Del uz by z, del z.
Yeah, exactly. This term goes to 0. That is because of the fact that your flow is fully developed. That is something that we wrote. What happens to this term? Is it 0 or a non-zero quantity? We just now stated something which is known as this axisymmetric condition. So the axisymmetric condition says is that your variables are independent of theta. If your variables are independent of theta, then of course their derivatives will also be independent of theta, which means that del u theta by del theta is also 0. This is because of the fully developed assumption. This is because of the axisymmetric, condition. Okay, which means I just have, so what I just have del del r of r u r to be equals to 0. Okay, now let's consider this r u r as some, let's say, u tilde of some function r, where u tilde of r is r u r, that's it. Where u tilde of r is just r u r. Okay, so which now means that therefore I just have del u tilde by del r equals to 0, which means that my u tilde so observe this carefully. Since del u tilde of del r is equal to 0, this means that my u tilde is not, so I can write that my u tilde is not a function of r. But what did we consider u tilde to be? My u tilde is just r times ur. And I say that my u tilde is not a function of r. So when is this possible? So how is this possible? Because I I just say from here that, so I got that del u tilde by del r is equal to 0. Okay, this clear. So the math says that my u tilde is not a function of r. The math is perfectly correct, and I consider my u tilde as, so what is u tilde? It's just the transformation that I have considered, that u tilde is just r times ur. So on one hand, it says that u tilde is not a function of r, but I know that u tilde is just r times ur. So when is these two cases, simultaneously possible? There is only one possibility that may arise here. Can you tell me? So how is this possible? Because see, had this been a non-zero term, then this term is always a function of r, because I have an r multiplied here. But this term says that u tilde is not a function of r, which means that the only possible scenario is that ur has to be equals to 0. Which means for this case, invoking all the assumptions, I should always have a 0 radial velocity. And this is also satisfied because there is something which is known as a no penetration condition. You must have ur equal to 0 on this surface and on this surface. Okay, and the only possible direction my velocities can vary, at least as I have seen for this problem, is that is in the radial direction, because we know that the velocity components u theta and uz are function of r. Okay, which means the only possible scenario for this case is that my ur should vary along the radial direction, but this is not possible because ur at these two faces are 0. Okay, so it's like ur can only vary in the radial direction, but I say that ur is 0 at the interfaces, which means that throughout the flow field ur has to be equal to 0. And if you don't believe this, then rigorously you can just show that your ur has to be equal to 0 from the continuity equation. I hope this is clear, which means I just now need to solve for, we need to solve for u theta as a function of r and uz as a function of r. That's all we need to do. Okay, I hope you understand what I meant to say in this context. So that's it. If you know what we need to solve, so the next step is, what do we need to do? We just need to apply Navier-Stokes equation in the cylindrical theta direction and and the z direction to basically get the flow field. That's it. So that's what we'll do. So we'll write the the Navier-Stokes equation in theta direction. Okay, this is a little bit long because cylindrical coordinates are a little bit nasty, so I'll just write it down. Please bear with me for a couple of minutes. So your Navier-Stokes equation in theta direction is something like this. It is rho times del u theta by del t plus ur times del u theta by del r plus u theta by r del u theta by del theta plus ur plus uz times del u theta by del z. Okay, this is the inertia term, and then I have minus 1 upon r del p theta del P by del theta plus the dynamic viscosity times 1 upon R del R of R times del Q theta by del R. Okay. All right. Plus 1 by R square del square U theta by del theta square plus del square U theta by del Z square plus 2 by R square del UR by del theta minus U theta by R square. That's it. That's, the full Navier-Stokes equation written, in theta direction. Now, you need to quickly tell me which term basically go to oblivion or which term basically go to zero. What happens to this term? Is it zero or a non-zero term? Please tell me quickly. I mean, is it zero?
It's a zero
Yeah,
steady state.
exactly. This is zero for a steady state. I already said UR is equal to 0. We just now proved here, which means this term is just 0. Okay. I said that. So what happens to this term? Is it 0 or a non-zero? Can you tell me?
That is a zero.
0?
Axisymmetric.
Exactly. It's 0 because of axisymmetric. Very nice. So this is 0. UR is basically equals to 0. This term is equal to 0 because of the fact that it is fully developed, as you say.
Fully developed.
Yeah. Can you tell me what is this term? Del P theta by del theta?
Uh, no,
Is it 0 or a non-zero?
non-zero.
Why is it non-zero? So this means that you are saying that your pressure can vary along the theta direction.
No, 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 no. It's a zero,
It's
zero, zero.
zero. Exactly, it's zero.
Yeah,
Because
yeah, yeah,
again,
yeah. I thought it's a dough as is it.
oh
Sorry.
no, sorry. Yeah, it's zero
This this
basically.
ca- this case is zero.
This is zero. That's again because of axisymmetry. If you have, so the very if your variables are independent of theta, that means all variables are independent of theta. That's the scenario. Okay. We will have a non-zero term. This is a non-zero term that we cannot do anything on this. This is again zero because of
Zero.
axisymmetry, and this is zero because of the fact that it is fully developed. UR is basically equal to zero, which means that I just have so the only non-zero things that I have is 0 equal to mu times. Of course, the mu will also get cancelled out because it will because the other half is just 0, which means I just have 1 by R times del R of R del U theta by del R. Okay, and I just have this term U theta by R square. I think that's it. Let me check my notes. Yeah. Yes, that's the term we exactly end up getting. Okay. Now, since u theta, since u theta is just a function of r only, okay, I can basically remove the partial derivative with ordinary derivatives. That's the most common thing that we do, which means I can just now write this as 1 upon r ddr of r times du theta by dr minus u theta by r square, and just apply the product rule. Just apply the product rule of differentiation. You will just get 1 upon r du theta by dr. I mean, you are masters of this now, so I believe you can figure out what did I just do. It just becomes d2 u theta by dr2 minus u theta by r square. This is equals to 0. And what I do is I just multiply the entire equation by r square, which means I just end up getting r square times d2 u theta by dr square, okay, plus r times du theta by dr, okay, minus u theta is equal to 0. That's it. That's the equation that u theta. So that's the equation that governs how u theta essentially varies with time. Okay. All right. So this equation is subject to what? So now can you tell me the boundary condition? What? So if you want to solve this equation, you need boundary conditions. So can you tell me what are the two boundary conditions for u theta? So just look at this picture. We have two cylinders that are basically rotating. Okay. So I know that at r equal to a and at r equal to b, the rotational velocity of the fluid is exactly equal to the rotational velocity of the cylinder, which means that I can write that at r equal to a, my u theta is, so here is the thing. Actually, so when I write the velocity, I should write u bar at r equal to a is actually omega, which is the rotation of the cylinder, okay, cross the radius. Omega 1 is the rotation of the cylinder 1 cross the radius a, and this is basically a times what I can write. I can just write it as er hat, which is the radial direction. Now, can you tell me what is the direction of omega 1? Can you tell me what is the direction of omega 1? What is, so omega 1 is a vector, you understand that, right? Because the angular velocity is, it's a vector essentially. So sometimes people call the angular velocity as a pseudo vector, but we will not go into all those things. But in principle, it has the property of vector. So if I have a cylinder that is rotating with some omega 1, what is the direction of this angular velocity? Can you tell me? So always understand that this is given by the right hand thumb rule. Okay, so if your omega is rotating in the theta direction, then your thumb points to the direction of the rotation. So your direction of your omega is omega 1, and it is in the ez direction because your thumb points. So if you curl your finger towards theta, your thumb basically points towards the z. That's typically what I want to say, which means that this is essentially, so your omega is essentially the magnitude of omega. Oops, so its magnitude is omega 1, I agree. Its direction is Ez. And then this is, so you are doing a cross product with this omega and the radial vector, which is a times er at r equal to a precisely. Okay. Now, so this becomes omega 1 a Ez cross er. So what is Ez cross er? So what is this? From the rule of cross product, Ez cross er is basically E theta. That is just the rule of cross product. So just like Ex cross Ey is Ez, Ey cross Ez is Ex, and the other way around, the cyclic things, which and just how it follows in Cartesian, it just simply follows the same in cylindrical space, which means your Ez cross Er is just E theta, which means that your velocity field at the cylinder surface is omega 1 E theta. And this proves that you essentially just have a theta direction velocity on the surface of the cylinder. And that's why I can just write crudely, and that's why people just crudely write that at r equal to a, your u theta is basically omega 1a. But this is how the math essentially comes from. Okay, it's just the cross product that you need to do, and you need to understand that in what direction does the rotational velocity essentially points towards. Okay, so that's the thing. So this is one boundary condition that I have, that at r equal to a, I have u theta equal to omega 1a. Similarly, if you do the same exercise at r equal to b, I have my u theta as omega 2 times b, because omega 1 is the rotational velocity of the inner cylinder, omega 2 is the rotational velocity of the outer cylinder. So okay, so these are the two boundary conditions. But now, how do we solve this? So we'll end this class by looking at, just by looking at how do we basically solve this equation, okay? And then in the next class, we'll see how to basically go into the z direction equation. Okay, so do you know how to solve this equation? First of all, is this a linear equation or a non-linear equation? Can you now tell me? Is it a linear or a non-linear equation? So R just, yeah,
It's linear.
exactly, it's a linear because R is not a dependent variable. R is an independent variable, to be precise. You are still multiplying the dependent variable with an independent variable. So this is a linear equation, and of course this is homogeneous because u theta equal to 0 also satisfies this equation. But the only difference between this and a more conventional, I would say, differential equation is that we have a variable coefficient multiplied with the nonlinear term. Okay, had this r square and r been constant, we will just take the form of u theta as some e power mx, substitute it here, you will just get something which is known as a, so I think you know this term, you will get a complementary function, something like this. Okay, you will just get an equation m square plus m minus 1 equal to 0. Calculate the roots of m, and just substitute it. So your entire solution will be e power m1x plus e power m2x with some constants a1 and a2. That's it. This was possible if you had these constants as, if you have these terms as just constants and not variables. But here this is an ordinary differential equation with variable coefficients. Okay, and these kind of equations has got a special name. These are known as Euler-Cauchy equation. Okay, these equations so this equation 1 has got a special name. These are known as Euler-Cauchy equation. And sometimes in the language of fluid dynamics, sometimes fluid dynamics like me and you, they also call this as equidimensional equation. Okay, I'll tell you why they call it as equidimensional equation. See, if you observe the dimension of this has got a dimension of length. So what is u theta? U theta is a velocity. So the dimension of this is length, is meter per second, which means length, which is L by T. Okay, what is the dimension of this? The dimension of derivative of this is L by, so its dimension is L by T by L, which is nothing but, it's nothing but what can you say? So if you just calculate the dimension of this term, okay, it just so happen that, let's see. So r has got a dimension of L. Okay, u theta by, so u theta has got a dimension of L by T, and r has got a dimension of L, which means that this and this L cancel out. This means that this term also has got the same dimension of L by T as this term. And similarly, if you do the exercise for this term, this has also got the same dimension of, L by T. Since these three terms has got the same dimension, that's why, sometimes these equations are known as equidimensional equation. But more, in the language of mathematics, they are known as Euler-Cauchy equation. Okay, and the solution to, and the way, the procedure to solve this equation is that you consider u theta. So you assume that u theta is some r power k. This is an assumption. So you're assuming this. So if you're assuming this, then you need to just substitute this form of u theta into this equation. Let's do it. Let's just do it and see what do we get. So if you do this, you just need to evaluate what is du theta by dr. It is just k times r power k minus 1, and d2 u theta by dr2 is k times k minus 1 into r power k minus 2. And then if you just substitute this u theta, its derivative and its second derivative into this equation, you will simply get, if you just do this substitution, we have, let's say, r square times du theta by dr2. It is just k into k minus 1 times r power k minus 2. Then the second term I have what? I have r times du theta by dr, which is r times k into r power k minus 1 minus u theta. U theta is just r power k, and this is equals to 0. Okay. Now, these two terms will combine and give me r power k. These two terms will combine and give me r power k, and this also I just have an r power k, which means I can just write it as k into k minus 1 r power k plus k into r power k minus r power k equals to 0. And if I take r power k as common, I just end up getting k into k minus 1 plus k minus 1, and this is equal to 0. And this is only possible if this term is equal to 0, because r power k cannot be equal to 0, because if r power k is 0, if this term is 0, this means u theta equal to 0, and that's the trivial solution. But we are not looking for trivial solution essentially. Okay, so whenever we get a homogeneous equation, we always end up getting a trivial solution. Okay, but we will see later on, there is something which is known as an eigenvalue problem, but this is not exactly similar to an eigenvalue problem. But you get, so if we get a homogeneous equation, we sometimes kind of tend to get eigenvalue problems, but this is similar to something that we do. But anyways, the point is that in homogeneous systems we always get a trivial solution, but we are not looking for trivial solutions, which means that r power k cannot be equal to 0. So the only possibility that we have is that k into k minus 1 plus k minus 1 is equal to 0. And from here, if you calculate the value of k, I think you will get k to be equal to plus and minus of 1. That's just straightforward. Right? Because from here it will be k square minus k plus k minus 1 is equal to 0. These two things will cancel. And from here, you'll get k square equal to 1, which means your k will be plus and minus of 1, which means that the solution of so you'll have two linearly independent solution. So you'll have u theta u theta as some a1 times r power 1, which is just r, plus some a2 times r power minus 1, which is just 1 by r. That's it. That's the solution for u theta. And this is how you typically solve an Euler-Cauchy equation, which is nothing but an ODE of variable coefficient, but the dimension of all the terms is just the same. And that's why sometimes they are called as equidimensional equation. Now, how to evaluate this a1 and a2? Just use two boundary conditions. We already have the boundary condition, which is this. So that's it. Just substitute these boundary conditions into this equation. I mean into this form, and you should get. So I just have the so I'll not do the substitution. This is now for you to figure it out. Uh, just substitute the values. That's it. But I'll just give you the results. You can just check it at your end. So your boundary so what you do is just substituting the boundary conditions. You should end up getting your a1 as omega 1 minus b square by b square minus a square into omega 1 minus omega 2. Okay, and a2 as some a square b square by omega 1 minus omega 2 times b square minus a square. That's it. You use the boundary conditions, get this a and b, and you know that your solution of u theta as a function of r is just a1 times r plus a2 times a2 by r, where your a1 and a2 are just this. That's it. That's the solution that you get of u theta by solving the theta direction equation. Alright, so we'll stop here today. This problem is not over yet. What we will do is, in the next class, we'll apply the jet momentum equation to basically get what is uz of r. And then I'll show you a very interesting consequence of this problem if we make certain assumptions on the rotational velocities of the cylinder, and we'll see something which is on the rigid body motion, uh, uh, based on we'll do some tweaks with the rotational velocities, and we'll invoke certain assumptions, not an assumption, certain special cases, and we will see the consequences of having rigid body motions in fluid. Okay, on this problem. But we'll stop here for today. If you have any questions, you can ask, or else we'll meet in the next week. Thank you for attending the question, and thank you for bringing up the thank you for attending the session. Thank you for bringing up the questions, and please actively participate in the discussion forum, and I'll be happy to clarify the questions as and when clarifications are required. If there are questions, you can ask. If not, we'll meet in the next week at the same time, in the same link. Thank you very much.
Thank you so much, sir.
Yeah, thank you. So I'll end this meeting.